This video is going to be on 2.3 velocity time graphs. It is going to look a little bit different if you were in class because I did change things to make it a little bit easier to understand. And this time I'm only going to focus on velocity time graphs for this lesson other than the do now. So the do now says describe the motion of this object in this graph. And well, if you take a look at this graph, this is a position time graph. Right? We know that this is a position time graph. And your y-axis is measured in meters, which means it measures how what your position is over time. So let's analyze what this graph is saying. Right, this graph is saying that from 0 to 4 seconds, you went from a position of 0 meters to a position of 8 meters. Right, so you're here, right? You're at a position of 0, and then 4 seconds later, you're at a position of 8 meters. And then for the next 2 seconds, you go from a position of 4 to 6. So you stay at a position of 8 meters, and you don't really go anywhere, right? So from 4 to 6 seconds, you're at rest, right? You're at rest here. So you're at rest here. And then from 6 to 8 seconds, right, you go from a position of 8 meters to a position of 16 meters. Well, let me draw this using a different color, right? So now you go from, well, it might be too similar. Let's use this. So you go from a position of 8 to a position of 16 in the next 2 seconds, right? So you go even further. Right, you go even further, and now you're at 16 meters. And I'm sorry, this overlaps. In hindsight, I should have made it smaller. So now you're at a position of 16 meters. And then what happens on the last 2 seconds? Well, from 8 to 10 seconds, you go from 16 all the way back to 8. And so you travel backwards 8 meters. And so now you go from 16 meters to 8 meters, right? And you traveled another 8 meters. And so that's what's happening in this graph, right? You go from the first 4 seconds, you go from 0 to 8. So you travel 8 meters. From 4 to 6 seconds, you're at rest. And then from 6 to 8 seconds, you travel another 8 meters. And then from 8 to 10 seconds, you go back, right? You're traveling backwards now, back to 8 meters. And that's a do now question. So, motion mapping. Now, let's say we have a toy car, right? I mean, we do obviously have a toy car here. We have a toy car, and it's going to the right. So and you can tell by the diagram that the car is speeding up. Well, now we want to draw the graph. Right? Let's say that our car starts with an initial velocity of 0 meters per second. And let's say our acceleration of this car is 1 meters per second squared. Well, what does this mean, right? What does that acceleration of 1 meters per second squared mean? Well, the definition of acceleration is rate of change well, let me just reword it. Rate at which velocity changes. So if your acceleration is 1 meters per second squared, right? Well, acceleration is rate at which velocity changes. It's also on the top of your papers, your notes. Then that means your velocity changes by 1 each second. So, and we start at a velocity of 0, right? So we start over here. And if your acceleration is saying that your velocity changes by 1 meters per second each second, right? So velocity is changing by 1 meters per second every second, well then what's your velocity the next second? Right? If your initial velocity is 0, and your acceleration is saying that your velocity is changing by 1 meters per second every second, what's your next number? Well, the next number is 1, right? The next second, your velocity increases by 1 meters per second, so your velocity is 1 meters per second now. And so, well, we're now at 1, 1. Well, if every second you increase by 1 meters per second, where are you at 2 seconds? Well, you're at 2. Right, and then the third second 3, and then the fourth second 4, and now you have a straight line. And so this is what it looks like for an object that's speeding up in the positive direction. Let's move on to the second one, right? Let's move on to 1b. And on the other hand, we now have an object slowing down, right? Instead of speeding up now, we have an object that's slowing down. And so the object starts with an initial velocity of 5 meters per second. So we're going to put our dot there. And our acceleration of negative 1 meters per second squared, right? That means that your velocity changes by negative 1 meters per second per second. That's how much your velocity changes each second, right? That's what acceleration is. It's changing velocity. The next second, if our velocity changes by negative 1 meters per second, well, 5 plus negative 1 gives you 4. And so now we're at the next second, we have a velocity of 4 meters per second. And so, and on, right, etc. Until we get to a velocity of 0. Right, we've now completely stopped and our velocity is 0 now. Which makes sense because we are slowing down. We are slowing down in the positive direction. Move on. So, like what we learned in PT graphs, the slope of a VT graph, it tells you something. Now, the slope of a VT graph does not tell you velocity because that's only for a PT graph. We learned that in PT graphs, the slope tells you velocity. But slopes in VT graphs do not tell you velocity. They tell you something different. And if you don't recall from the previous lesson that, well, your slope is, right, we calculate for delta y over delta x, which is essentially your change in y, right? How much your y changes versus how much your x changes. And your y is this, right? And your x is that. So this is your x-axis and this is your y-axis. And let's figure it out, right? Let's figure out what our slope tells us. So the y-axis on a velocity time graph gives us velocity, right? This is on the y-axis. On the x-axis, you have time. So you have time on the x-axis. And so, well, what is your slope? Well, you know your slope is your change in y over change in x. So it's delta v, right? Or delta y over t. And I'm going to neglect the delta there, okay? I'm not going to tell you why I'm neglecting the delta, just that I am. Actually, I might as well keep it. Delta t. And which formula looks like that on your reference table? There's a very specific formula on your reference table that looks like this formula. I'm going to tell you, right? It's this. It's acceleration is equal to change in velocity over change in time. Which is literally the definition of acceleration, right? Acceleration is the change in velocity over time. That's a literal definition of acceleration. And so we can say that the slope on a VT graph only is very important. On a VT graph only represents acceleration. So the slope on a VT graph only represents acceleration. Okay. Do this. So let's do the practice question, right? So let's say 2b was the acceleration of this object at a time of 2 seconds, right? So you want to know what the acceleration is at that point in time. Now, when they're asking you what the slope is, right? Because again, the acceleration is the slope, so we want to calculate the slope here. When we do this, we're going to take the slope of this entire line. So if this coordinate is on this line, we take the slope of this entire line. So let's calculate the slope of this line. Right? And actually, we don't even need to do that. We can actually just calculate the slope from here to over here, right? And that's good enough. So the slope, again, is acceleration. Since we want acceleration, we want slope. So on a VT graph, right? It's on a VT graph only. So delta y over delta x. Your change in y here from 0 to 5, your change in y is 5. And your change in x, right, from 0 to 2 is 2. So 2.5 meters per second squared. And that's your answer. Let's move on to the second practice question. So what is the acceleration of this object at a time of 6 seconds? Now this is a little bit trickier because, well, the point is on 6 seconds. And since the point is on this line, we have to calculate the slope of this line right here. So what is the change? So let's actually start at 4 seconds. So now we can calculate the slope of this line, right? Because we do want acceleration. So slope is delta y over delta x. What's delta y? Well, is your y changing here, right? No, we're not. Because here it's 10, here it's 10. There's no change, 0. And your change in x from 4 to 6 is 2. So 0 divided by anything gives you 0. Which makes sense because you see that your velocity is not changing here, right? From 4 seconds to 6 seconds, you don't have a change in velocity. And if you don't have a change in velocity, you have no acceleration. Your acceleration is 0. All right. Do another practice question. So what is the approximate acceleration of this object at a time of 4 seconds? So they want to know what the acceleration is at 4 seconds here. Again, because the coordinate is on this line, we're going to calculate the slope of this line only. And I'm actually going to start at 3 seconds right there. We'll start at this dot right here. So again, you want to calculate the acceleration. So you're going to calculate slope, and this is on the VT graph only. So slope is equal to delta y over delta x. Delta y, what's a change in y? So you go from 20, right, and you go to 10. And so your change in y here is negative 10, right, because you're going down 10. And your change in x from 3 to 4 is 1. And so you get negative 10 meters per second squared. And then let's do the next practice question. What is acceleration of this object at time of 9 seconds? So you're over here. So we want to calculate the slope of this line right here. But we know from the previous questions that, well, if you have a straight line and while you're staying at negative 20, well, your velocity is not changing. So delta y is equal to 0. It doesn't matter what your delta x is at that point because 0 divided by anything is 0. All right, let's move on. So in our average velocity formula, right? So in our average velocity formula, we have v bar is equal to d over t. And well, guess what we can do in a velocity time graph? We have v, we have t, so we have basically 2 of these variables already. Well, what do you think we can do? Well, we can use those 2 variables and we can solve for d. So if we solve for d, we multiply t on both sides. Well, t's cancel out, and then what we get is this. So we get VT is equal to D. So we can, but in a velocity time graph, what we can do is we can figure out what our distance or displacement is. Well, how do we do that? Well, what we do is we just do the area. So the area in between the line, right? So that's, remember, area of a rectangle is width times length. And the width of this graph, right? The width is your y-axis, which is velocity. And your length is your x-axis, which is your time. Well, that's essentially saying area, right? So if area is width times length, and if width is v and then length is t, well, then area is vt. And if we know that d is equal to vt, well, we can just say a is equal to d. And I'm substituting here. All right, so basically, and if you weren't following, just know that, well, the area in between the line and the x-axis tells you distance or displacement in a VT graph only. Now, obviously, we need to do some practice problems before you guys fully grasp what's happening here. So the question says, what is the displacement of this object from 0 to 1 second? All right, so we want the area in between the line here and this right here. Right, so we want to calculate the area of this triangle from 0 to 1 second. Right, they're asking you for displacement on a VT graph. So we need to calculate area here. And then the area of a triangle, if you guys recall, it's 1/2 base times height, right? That's the area of the triangle. What's my base here? Well, my base is 1. I'm going to do 1/2 is equal to 1. And what's my height? Well, it's 10. So my height is 10. And so when we do the math here, 1/2 times 1 times 10, we get 5 meters. Let's do the second question. So what is the displacement of this object from 2 to 4 seconds? So let me use a different color. So now we want 2 to 4 seconds, and so we want to calculate the area underneath the line and above the x-axis. And well, how do we do this, right? It's an irregular shape, so we can't really use like a specific formula. Well, how do we calculate the area? Well, we're going to calculate the area by splitting this graph into 2 sections. Right, so we're going to do this. We're going to calculate the area of the square first. And then add the area of this triangle, and then we get our total area. So let's do that. So the area of the square, right, it's width. So the area of the square, width times length. So we're width. Your width is 20. Your length is 2. So we get 40 here. Your area of your triangle is 1/2 base times height. So 1/2 base, again, your base is 2. Your height of this triangle is 20, right? So you're going from 20 to 40, your height is 20. And here it's 20 meters. So your total displacement, right? Now we need to add the areas. So it's square plus triangle, 40 plus 20 gives us 60 meters. That's our answer. We travel 60 meters here. Okay. Next practice question. So what is the distance traveled for the first 4 seconds, right? So again, we want distance traveled, and this is a VT graph, so we're going to do area. That's area. Right there. We want area traveled here. Right, so areas of this triangle is 1/2 base times height. Your base is 4. Your height is 10. And so we get 20. And that's the answer for there. And the second question was, what is the distance traveled for the first 5 seconds? Well, since we already calculated the area of this triangle, we don't have to do it again. And then they want first 5 seconds now, so they want all the way here. They want up to here. So the only thing we need to do at this point is calculate the area of this rectangle and then add it to our triangle. So let's do that. So area of this rectangle is width times length. My width is 10. My length is 1. So 10 times 1 gives me 10. And now we need to add the areas. So 20 plus 10 gives me 30. And that's the answer. Right? My total distance traveled for the first 5 seconds is 30 meters. Alright guys, hope that was insightful.